In this lecture, we explore some of the ways that mathematical ideas appear in fiction. We'll go with Gulliver to Brobdingnag and Lilliput, we'll visit the giant spiders of Hogwarts, we'll chat with the king of Lineland, and we'll even drop in on Captain Ahab. But we'll begin with Lilliput and Brobdingnag. One of the ways we can understand whether the giants that we find in Brobdingnag or the Lilliputians from Lilliput are really possible in real life is to use a mathematical principle called the square cube law. And I think it's okay to analyse these things, even though, of course, Jonathan Swift's satire is not asking us to really believe in these large and small lands, because he mentions mathematicians in the book. He mentions what the Lilliputian mathematicians calculate in terms of what Gulliver eats. So I think it's fair game to explore how realistic these things are. So when we're talking about giants, can they exist? The key principle is what's called the square cube law. So here it is. When we scale shapes by a factor of k in all dimensions, length, width and height, the areas involved increase by a factor of k squared and the volumes by a factor of k cubed. And you can see in the picture on the slide, I've got a cuboid there and I've shown doubling all its length, width and height. And so say the cross-sectional area would increase by a factor of 4 in that case and the volume by a factor of 8. So that's a square cube law, and that's been known since, Galileo. How do we apply it to giants? Well, when we walk around, our bones obviously have pressure put upon them by our weight, and that pressure is given by the force on the bones divided by the cross-sectional area of the bone. So as we have seen, the area, cross-sectional area, if you scale up somebody by a factor of k, that area would be scaled by a factor of k squared. What about the force? Well, Newton's law tell us F equals ma. The force is mass times acceleration. Acceleration due to gravity on Earth is about 9.81. The mass, of course, will be proportional to your volume. Okay, so that means pressure on your bones is proportional to your volume divided by your area. And we've just seen that with a scaling factor of k, that volume increases by a factor of k cubed and the area by k squared. So if we cancel out that, then we get that the pressure is proportional to k cubed over k squared, cancel the k's, and you just get a factor of k. Now, this is bad news for our Brobdingnagians. They are 12 times our dimensions. So this means that the pressure on their bones is 12 times what it is on ours. Unfortunately, human bone can only actually take about 10 times the standard pressure. So the Brobdingnagians' bones would break as soon as they tried to walk. Someone like Hagrid, who is shown here, he's the gamekeeper at Hogwarts School of Witchcraft and Wizardry. He has a better time of it because he's actually only a half giant. And he's described as being twice our height, but 3 times our width. That means that his volume is 18 times ours, and his area, the surface, cross-sectional area of his bones will be just 9 times ours. So he has twice the pressure on his bones. So he can walk around. He's just going to be a bit more prone to broken ankles and things like that. Now, I've mentioned the gravity on Earth because there's another satirical work by Voltaire called Micromega, which features a giant from somewhere near Sirius. Micromega, and he visits Earth. Of course, he couldn't exist on Earth because he's so huge. We'll see in a second from this quote. But could he exist on his own planet? Now, the quotation tells us how much bigger he is than we are. He's 120,000 feet tall, and compared to us, about 5 feet tall, says Voltaire, which was about average at that time. So he's got this quote where he says that actually the geometers are going to conclude, some editions it says algebraists, are going to conclude that since our own sphere is 9,000 leagues around, it is absolutely necessary that the sphere that produced him, his planet, was 21,600,000 leagues around. So, or times greater than ours. Now, actually, if the scaling factor of 5 feet to 220,000 feet, that's 24,000. So if they've just multiplied 9,000 by 24,000, actually that's the wrong answer because that would be 216 million. So these geometers are clearly one of the more ignorant geometers of the world that are being satirized in this book, or maybe Voltaire couldn't do his multiplication correctly. We'll never know. But this doesn't really work in terms of being bigger, because let's think what happens to gravity on such a planet. On planet Earth, and in any planet, we can work out what the gravity is at the surface using the rule, as shown, that the gravity on the surface is given by, there's an inverse square law, so it's inversely proportional to the square of the radius of the planet. And what's on the top there, you've got that big G, that universal gravitational constant, and then you multiply by the mass. And of course, the mass of a planet is proportional to its density times its volume, right? So the volume depends on the cube of the radius. So what we end up with then is that the gravity on the surface of the planet is proportional to the density of the planet times its radius. This means if the Syrian planet is like ours, but just 24,000 times as big, then the gravity would be 24,000 times as much. And Micromega would be in even worse state than he would be on planet Earth. Okay, but maybe his planet is less dense. Well, astronomers tell us the least dense planets in the universe are these so-called super puff planets. Even they are 1% of our density. So even their gravity on a big planet like this would be 240 times ours. So really, Micromega cannot exist, and certainly not on a planet described by Voltaire. So that's big people. What about little people? Well, again, we know exactly how big the Lilliputians are, which is one reason to focus on this book. So Gulliver says that the king of Lilliput has to work out how much food they're going to give him, and His Majesty's mathematicians work out that he's 12 times as big as them in every direction, and so they work out that he must need 1,724 times as much food as the Lilliputians. So to begin with, let's think. They're 12 times as small as us in every dimension. What is life like for the Lilliputians? We'll come back to that 1724 number in a minute. So lots of films and stories where you have tiny people feature them in perilous situations where they might fall from something huge like a kitchen table or something like that. And there's all this jeopardy and fear. Let's see what happens when a tiny person falls. So when any object falls, there are two forces on it. So one is the force due to gravity. So again, force equals mass times acceleration. So the force downwards will be your mass times g, acceleration due to gravity. But then upwards counteracting that is the resistance of the air to you falling through it. And that is proportional to the velocity at which you're falling and to your area, the surface area that you're showing. And that's, of course, why we have parachutes to increase the surface area and stop us falling so fast. Because we reach a limiting velocity called the terminal velocity, which is when those two forces balance out. So when you're going fast enough such that the air resistance balances exactly out the force due to gravity downwards. At that point, you've got the terminal velocity v. If mass times gravity is equal to the air resistance, which depends on the area, the terminal velocity v is proportional to your mass divided by your area. It's that square cube law coming in again. That velocity will be therefore proportional to the scaling factor of the creature. Okay, so our terminal velocity as humans is about 50 meters per second, which is quite fast. But a Lilliputian, you've got to multiply that by the scaling factor, which for the Lilliputian's case is 1/12. So a Lilliputian's terminal velocity is 50 times a 12th, which is about 4.2 meters per second. So they actually reach terminal velocity much sooner. Now, a human wouldn't be hurt by a fall at that speed. But what about a Lilliputian? They're much smaller. What happens there? Well, of course, it's not the fall that hurts you. It's the landing, because you've got this big amount of kinetic energy that you've accrued, and it's got to be dissipated over the surface area that contacts the ground. So kinetic energy, we know, is half times the mass times the velocity squared. And at the point of the maximum kind of survivable velocity, that whole energy is dissipated over your area. So when you reach that maximum survivable velocity, that half mv squared has got to be proportional to the surface area. So again, your area is going to change with the square of your scaling factor. So if we just divide through by the mass here and get a bit of proportionality going on, we find that the maximum survivable velocity for you as a small person is proportional to your surface area divided by your mass. And that is actually, it's a square cube law, but upside down, that'll be 1 over the scaling factor. So for a Lilliputian, 1 over a 12th, that's 12. So their survivable velocity will be root 12 times ours. Now ours, NASA did some calculations, ours is about 12 meters per second. And so for a Lilliputian, you have to multiply that by root 12. So they have a better time of it. And theirs is about 42 meters per second. So this means, if we think back, what's their terminal velocity? It was 4.2. But they can actually survive 42 meters per second. They can survive a fall from any height. So Lilliputians falling is absolutely no danger to them. This is true of all these little characters. You know, there's a B-movie characters, and the picture shown on the slide is of a still from Dr. Cyclops, where the evil scientist shrinks down these poor innocent people. You know, and she's, well, I can't fall off this chair. Yes, she can. She'd be fine. And another thing that happens, Lilliputians and tiny people can actually jump quite high because the power needed to jump is proportional to your mass, but your muscles are generating power proportional to their mass. So actually those scaling factors kind of cancel out. And however big or small we scale you to, you can jump to the same fixed height. So humans can jump, say, a meter into the air, so can Lilliputians. They can jump up onto Gulliver without any problem. They don't need ladders or anything like that. So that's falling and jumping. Another consideration that we can make about the Lilliputians is about what they are eating. And here is where Clives Law comes in. So remember the Lilliputian mathematicians did that calculation about how much energy Gulliver needs. So your metabolic rate is the amount of energy you use per day. We normally measure it in calories. And the Lilliputian mathematicians clearly decided that the amount of energy, the amount of food you need to take in should be proportional to your mass, which kind of makes sense. You have internal organs and all that kind of thing. So they did the calculation. Okay, his mass is 12 cubed times hours. Well, that's actually 1728, not 1724. So either they made the mistake or Gulliver did, or Jonathan Swift did, or Jonathan Swift's printer did. Somebody made a mistake there. But the correct answer would be 1728, 1728, if that's the rule. The problem is, it isn't the rule. It's not the rule. You see, we lose heat from our bodies. We're warm-blooded creatures, and a lot of the energy use that we go through is by keeping our bodies warm. And we lose heat from our bodies in proportion to our surface area. Now, that is not growing with your mass, which grows with your volume, but with your area, and that's got that squaring factor to it. So actually, if we think it's to do with heat loss, how much energy we use, then we might predict something like mass to the power 2/3, not mass cubed. The real answer seems to be somewhere in between that. And this is now known as Clives Law, because Clives was a scientist who first did lots of experiments on the metabolic rate of different sizes of mammals, right from sort of mouse to rat to dog to cat, human, horses, elephants. So a whole range. And he plotted the outcome on this logarithmic scale and showed that actually it seems to be that your metabolic rate, the amount of energy you use, is proportional to your mass raised to the power 3/4, which is indeed between 2/3 and 1. So based on that, if we had a human-like creature and we scaled up by a factor of k or down, then remember the mass is increasing with k cubed. So we take that k cubed, raise it to the power 3/4, and we get k to the power 9/4. And that's what we have to multiply the human energy use by to get the energy use of a tiny person or a big person, scaled by a factor of k. So a Lilliputian then would need 1/12 to the power 9/4 times the human calorie intake, which is about 2,500 calories a day for someone like Gulliver, a man. That comes out at 9.3 calories, tiny. This is all very well, except Lilliputian food is also tiny. Now, calories in an amount of food is proportional to its mass. 10 grams of butter has 10 times as many calories, sadly, as 1 gram of butter. So the food calories that are contained in those tiny Lilliputian foods are going to be much smaller. Our normal apple, for example, is 100 calories, but a Lilliputian apple would only be about 0.057 calories. So Gulliver can get by on, say, 25 apples a day, a bit of a boring diet, but that would be enough for his calorie needs. But the Lilliputians, their tiny apples contain proportionately much less energy than our big ones, because it's that 1,728 factor that you have to divide by. So they need, you can work it out, 160 of their apples every day to meet their energy requirements. And you can do it more generally and work out that they'd actually need about 6.45, 6.5 times as much of their food per day as we need of our foods. You know, if we're eating a steak, they would need 6 of their tiny steaks to get the same amount of energy compared to what they need. So this is really bad for them because like their whole economy is going to really struggle because they're going to be having to eat 6 times as often as us. We eat 3 meals a day. They're going to need 18 meals every day. They're going to spend the whole time being hungry, looking for food and feeling cold. So the Lilliputian life is going to be really difficult. Another problem for Lilliputians and tiny people is what happens if you go swimming or get wet or take a bath, something like that. The problem is that all liquids have a surface tension, you know, a meniscus that we see, and any object immersed in, say, water, whatever the size of the object, will come out covered in about 0.5 millimeter thickness of water, a film of water all over its body. That's irrespective of the size of the object. So that means the amount or the weight of the object, the weight of the water that is on that little person or big person is going to depend only on its surface area, because you've got this constant thickness, the 0.5 millimeter, that does not grow or shrink. That's constant to do with the surface tension of the water. So a human coming out of the bath will be covered in this little thin 0.5 millimeter thick film of water. It basically weighs about 900 grams. It's nothing, it's negligible. But for a little person, we've got to scale that according to their surface area, which varies with the square of the scaling factor. And that starts to be a huge proportion of their weight. So taking the film Honey, I Shrunk the Kids, right, where the inept scientist accidentally shrinks his children to a 200th of their normal size, you could work out that they will weigh about 9.4 milligrams. But unfortunately, the water on them, as they come out of, in this case, a bowl of cereal, as shown on the slide, the water would weigh not 9.4 milligrams, but 23 milligrams. So that they would just completely be drowned by this. And you cannot swim around in a bowl of cereal if you are that small. Another issue is rain. Don't get caught in the rain if you're small. So here we see Arrietty from the Studio Ghibli film. She's sheltering under a leaf quite sensibly when it rains, because, raindrops are about 5 millimeters in diameter. You can work out the mass. It's tiny. But for a borrower who is about 1/16 of our size, that would feel like 250 grams would feel to us. Imagine being constantly pelted with large potatoes or something. That is not a pleasant experience. So they really need to keep out of the rain. Okay, so we've seen how big and small humans are going to cope, and not very well usually. How does this go with the animal kingdom, though? Because we do get very large and very small animals. Well, of course, it's fine, because animals are not just shrunk up or down versions of each other. An elephant is not just a large mouse. And Galileo pointed this out. He said little bones of small creatures, when you make bigger creatures, they are proportionately much thicker. They're differently shaped. So that's how nature adapts. Mammals, of course, have issues around heat loss, so you don't get very small creatures in cold climates because they're losing too much heat. You get Arctic hares, but you don't get Arctic rabbits. So we have these issues, but nature solves them by making animals different shapes, of course. If we think about things like birds or flying creatures, so there are various mythical flying creatures that we have, like Pegasus, the flying horse. Now, with birds, there's an issue around the size of their wings because of something called wing loading. That's the main consideration. The wing loading of a bird or any flying creature is its mass divided by the area of its wings. So already we can see, square cube law might come in again. Now, it's been found by lots of experiments that the maximum theoretical you could really have size of the wing loading is about 25 kilograms per meter squared. If you were to just take any old bird, you might see sort of giant eagles in fiction. If you just scale up an eagle, say, by a factor of k, then you can see that the wing loading will also be scaled up by this factor of k, because the mass over the wing area will still leave a factor of k on the top. So at some point you reach this maximum and you cannot just scale up birds. And of course, nature does not do that. An eagle looks different from a wren. What about a flying horse? Well, you can work out what the maximum would have to be for Pegasus to be able to fly. Just putting in the wing loading of 25 kilograms per meter squared, and say a horse weighs about 500 kilograms or something like that, he would need a 40-meter wingspan in order to be able to fly. I mean, that's a pretty big stable he's going to need. He certainly would not look like this statue. The biologist J.B.S. Haldane pointed out that angels would have to look pretty amazing. An angel with muscles that develop no more power weight for weight than an eagle or a pigeon would have a breast projecting for about 4 feet to house the muscles engaged in working its wings. So, these things, angels, if they exist, are definite proof of divine intervention. There's another little consideration when we come to think about large insects or arachnids. So we see sort of giant ants in the 1950s B-movie Them, about radioactive ants that grew to 10 feet tall. The picture on the slide is of the spider Aragog, who sadly died in one of the Harry Potter films. He is, of course, a vast spider. Could he exist in real life? Well, I mean, no. Already just the size of him would give his exoskeleton a bit too much work to do, especially when he sheds his skin periodically. But there's another problem, which is breathing. So insects breathe through tracheae, which are sort of little tunnels. The air diffuses through tiny holes in those called spiracles. And again, the square cube law causes problems, because the oxygen our bodies need is proportional to our volume. But the oxygen that is diffused through these tunnels is proportional to the surface area of the tunnels. So one will grow much more quickly than the other. The volume growth will be proportional to the cube, the surface area to the square. So Aragog is going to suffocate. Maybe that's what killed him. Larger creatures have lungs, of course, we have lungs, and that helps with this problem. I should mention that in prehistoric times, insects got much larger than they do now. One reason for that is that there was a lot more oxygen in the air. 30% of the air was oxygen 70 million years ago. But also there were fewer things to predate on them. And now we have big birds, and even back then pterodactyls and stuff came in that could predate on the big insects. And so it was safer for them to be smaller. Now, a lot of these considerations around growth are also applicable in the context of man-made objects. So there are some real-world applications to these considerations. I'm showing on the slide here a picture of two airplanes, and they are the smallest and largest commercial aircraft that are passenger planes. So on the left there's a Boeing, on the right there's the Airbus A380. Now the Boeing, if you were to just scale up all its dimensions so that it was the same size as the Airbus, which I will do now, you can see straight away that the wings on the Boeing are much slenderer than the wings on the Airbus. And this again is because of the square cube law. When you say double the size of everything, say the Boeing, it's about 2.2 times the scaling factor, but let's say it was 2, then when you doubled up the sizes, the volume and therefore the mass would multiply by 8, but the wing area would only multiply by 4. So it kind of half what you actually need in order to maintain that wing loading. So as you can see, the Airbus, its wings are much thicker proportionately, and that is why. And if you do the calculations, you find it's almost exactly matching the growth in the volume. Another consideration of the square cube law is when you're dealing with prototypes or models of machines. So in this slide on the left, you're seeing the Newcomen steam engine, which is an early steam engine that was used to pump water out of mines and things like that. And it worked by repeatedly heating and cooling a cylinder, and with steam and with cold water. Now, it wasn't a very efficient engine. It was okay, but it wasn't very efficient. And one of the problems was the inefficiency caused by the heat loss of this cylinder as it kept being heated and cooled. Now, heat loss, of course, is proportional to surface area, and the power that the machine produces is proportional to its volume, roughly speaking. So when Glasgow University had a model of this made, the problem of the heat loss causing this inefficiency was exacerbated because when you shrink down, the volume shrinks down faster than the surface area shrinks. And so actually this problem became so much more severe in the model that the model did not work. Now what they did was to bring in a young instrument maker called James Watt to have a look at this and to get it working again. And he realized the problem. And in fixing the problem and trying to get the model working, he actually came up with a much more efficient design for a steam engine, which of course is why we know the name of James Watt nowadays. So that's just some of the ways in which this simple idea of can giants exist and is Lilliput real can lead us onto some really fascinating considerations. Our next starting point then is to talk about dimensions, and for that we need to talk about Flatland. Flatland is a curious short novel written in 1884 by Edwin Abbot, who's shown on the slide there. Edwin Abbot, and he was the headmaster of City of London School in London. He'd also attended that school as a pupil himself. He wrote lots of books, but this is the only one really anything like this. He wrote about, philosophy and religion and other things like that, literature. This is unique as a book. Flatland is described as a romance of many dimensions. The protagonist is A Square, so this is Abbot, and he lives inside a completely two-dimensional universe. Now, the book itself has two roles, really. It's a satire on Victorian values, and in particular, the treatment of women and the kind of lack of educational opportunities for women. In real life, Edwin Abbot was very much a proponent of furthering opportunities for women in education, but also upon the kind of restrictive, dogmatic climate where there were people who said this is the way religion must be, and Abbot himself was much more in favour of a broad church approach, which did not have the extremes of the high church or the low church. So those are some of the satirical themes that come in the first part of the book, in part 1. But then the second part of the book is an exploration of different dimensions. So in the second part of the book, our protagonist, A Square, is astonished by a visitor from Spaceland, which is a 3-dimensional world. So there's sort of two aspects to this book. And we can discuss these. So I want to show you just briefly a couple of diagrams from the picture, from the novel. So on the left on the slide, you can see this is a diagram that shows the shape of the houses in Flatland. So Flatland is inhabited by polygons. All the people in it are polygons. And the men, they are either triangles or squares or pentagons or higher number of sides of their polygons. All the women are lines. So that's already not great. So they're not even two-dimensional, the women. They are lines, and then they have different entrances. The women have different entrances into the houses than the men. Your social class and your social standing and what your job is as a man in this society is determined by your shape. So sort of at the bottom, the lowest classes of workmen and the least skilled labour, the soldiers, they are isosceles triangles with a very kind of narrow vertex at one end, very pointed. If you're a soldier, it's very useful to have a pointed end, and then two equal angles at the bottom. And if you work hard by diligence and doing what you're told and all those kind of things over the generations, gradually your top angle gets bigger and bigger and bigger until you become sort of respectable working class person. And then the wonderful day when a son is born who has a 60-degree angle at his top vertex, and then of course he is equilateral, then he's into the ranks of being a respected person. So equilateral triangles are kind of the start of the, I guess, gentleman. And then in every subsequent generation, if you behave yourself, of course, then the family will produce a succeeding number of vertices. So the son of an equilateral triangle is a square, the son of a square is a regular pentagon, and then regular hexagon, and so on. So you get these regular polygons increasing in number of vertices, number of sides, until that the top, the priestly class, are referred to as circles, although they're not actually circles, they're polygons with a very high number of sides. And the great circle, the highest priest in the land, is decreed to have 10,000 sides, but no one, of course, would ever dream of measuring such a thing. So in Flatland, there are various rules about behaviour. Women in particular are very restricted because, of course, they are very dangerous. If you're walking along, you can't actually see a woman really from behind. She's got, maybe a point at each end. You can't see her. And so then what if she were to crash into you and stab you to death? So women, when they walk around, have to do this sort of little wiggle, and they have to constantly be, when they're out of doors, making a peace cry, it's called, so that people can hear them coming. Triangles obviously can cause damage, but the wider your angles, as happens in polygons, the safer you are. So we have various rules of behaviour. You're not allowed in any way to disguise your shape. For example, you're not allowed to paint yourself to cause yourself to appear by the different shadows a different shape. Houses are decreed that they have to be pentagonal, because a square house or even a triangular house, its angles will be too sharp, and again you could cause injury. So houses are pentagonal. There's a little not very good pun in the diagram of the house shown, because at the top you've got sides A and B, this side AB at the bottom, but at the top of the house you've got side R, the vertex R, and then O, and then F, and of course so RO and OF, roof, make the roof. Okay, so this is what the shape of the houses are. And now there's a discussion, of course, given that social structure and social values are so important in this society, of course it's imperative to be able to tell if you're talking to a hexagon or if you're talking to a dodecagon, a 12-sided shape, or even, a circle. So there's some discussion in the book of how you can actually tell people apart. And of course, if you were just on a plane and you could only see on a plane, you can only see lines, really. So how on earth are you going to tell whether you're talking to a hexagon or to a square or to a dreaded isosceles triangle only? Well, luckily in Flatland there is this fog which can give you distance. So there's depth perception that added. So you don't just see a line. You might see a line, but then two lines either side of it that are sort of receding into the distance. And by the amount or the speed with which they recede into the distance, so they're getting fainter and fainter as they get further and further away from you, you can discern what angles there are involved. So if you're looking at a regular pentagon, say, you might, from point on, you might see these two sides that are receding into the distance, but they will be receding quicker into the distance than if you're looking at a square head on. with his right angle. So you can do this depth perception and you can discern people apart because of this fog. Now, the second part of the book is perhaps mathematically more interesting because in that part, it begins with a dream where Square has a dream of Lineland, and he goes to visit the king of Lineland. And of course, in Lineland, where the world is completely one-dimensional, you have lines so that the men and boys are lines and the women are points, just as like in Flatland. And when you live on a line, you can only see points. So you can't see lines, you can't tell how long other lines are. You can see points, and you can't cross over each other. So you're condemned forever to be at that particular point in the line. That's a strange universe. But the king of Lineland, he cannot accept when Square says to him, yes, but I come from a two-dimensional world, and tries to explain what a two-dimensional world would be. The king of Lineland just doesn't understand what he's talking about. And Square, the king can hear this voice, but can't see Square. So Square enters Lineland. And so, of course, when a square intersects a line, it becomes the intersection part is a line. The king of Lineland can just see this point that suddenly appears, and then Square moves through the whole of Lineland, and the point is there, the point is there, the point is there, and then when Square comes out of the other side of the line, the point disappears. So the king can just see a point that appears for a bit and then disappears. He has no idea what's going on. He can't understand. Of course, Square is very condescending. Oh, what a fool. He doesn't understand that there's another dimension. So then it all comes back to him when suddenly there's a visitor from Spaceland. And the visitor from Spaceland is a sphere. And Square is just sort of sitting in his house one evening, and suddenly he hears this voice, and then this circle is there in his house. How did he get into his house? He didn't come in through the door. He didn't come in through the roof. How did he get in? Well, as Sphere explains, he has got another way in. He can come in kind of through the top, not through the roof, a different top from a different place. And Square is very confused by this. And there's a diagram in the book that says, first of all, the sphere, he's fully there with his widest parts of at his equator is intersecting Flatland. So then Square sees a large circle, thinks it's a priest and is very respectful. Then the sphere rises up, and the circle gradually gets smaller and smaller, and Square's what magic is this? And then, of course, as he leaves, he goes to a point and then he disappears without exiting through any doors. It's like magic. And Sphere tries to use the same analogy with Square that Square tried with the King of Lineland about different shapes and about, can't you imagine there's a different direction and I'm moving in through this different direction? He shows him moving in and out of Flatland, but that's to no avail. So the next step is to say, okay, I'm going to explain what this third dimension is to you by analogy. So you can imagine 0, 1, and 2 dimensions. Let's talk about what 3 might mean. He says, okay, this is Sphere explaining to Square. You know that 0-dimensional shape, that would just be a point. And then 1 dimensions, you kind of get lines. In 2 dimensions, you have things like yourself, a square. So those are the sort of shapes. So there's something in 3 dimensions, which I call a cube, but you have no name for it yet. So let's see what this cube thing might be like. So Sphere explains, okay, a point. How many terminal points does it have? Well, 1, because it's just itself is a point. So we now think of terminal points, we would say vertices. What about a line? So it's got a point at either end. So it's got 2 terminal points. And then what about a square? It's got 4 vertices, 4 terminal points. Okay, so then this cube, whatever it is, let's see. Well, this is a pattern, 1, 2, 4. Everybody knows the next number in that sequence is 8 because it's just doubling each time. So 8, that's the next number in the sequence. There's another thing we can look at about shapes. Bounding sides is what it says in the book. So we sort of think of these as things 1 dimension down that limit the shape in some way. So say for a line, it's actually a line segment. It's limited by these 2 points at the end of it. What about a square? Well, it's limited by the sides, the 4 sides. And a point, it's not limited by anything. It is its whole universe. So the sequence there that you have is 0, 2, 4. So the next number in that, this time it's an arithmetic progression, you're adding 2 each time. So you'd expect this 3-dimensional shape to have 6 bounding sides. Well, how can we make this 3-dimensional shape? Well, again, there's an analogy. So to make a line, you take a point and you just extend it in space And so you have 2 points, you join them together, and that makes a line. How about you take your line and you move it in space in a sort of perpendicular direction, another dimension, and that gives you a square. So you take your line, move it, and you make another line, and that's a square. So to make a 3-dimensional shape, obviously you take a square, you move it in a direction perpendicular to itself somehow, and you move it, and you join those 2 squares together, and you get a cube. So we all know this in our 3-dimensional world. Wow, this is surprises a square. He doesn't really believe. It's like, well, it's just meaningless stuff. But Sphere takes him out eventually of Flatland, and he sees it with his own eyes. He sees Flatland. He can see Sphere. Sphere can see inside, of course, a square because he's looking above it from the 3rd dimension. This is just an amazing thing. And eventually, Square comes to accept the gospel of the 3rd dimension. He goes back and preaches it to his fellow Flatlanders. Unfortunately, they don't believe him and throw him in prison, but there we are. At one point, though, Square then says to Sphere, this is fantastic. Thank you for showing me all this. Now let's see about the 4th dimension. Can we go there and have a look? Can I look inside you, Sphere, from the 4th dimension? And Sphere says, no, that's ridiculous. No, don't be stupid. But Square persists and says, okay, there could be a 4th dimension, and we could just follow the same rule you said. We've got this terminal points thing, 1, 2, 4, 8. So some sort of weird 4th dimensional cube would have 16 terminal points or vertices. And then if you take your 0, 2, 4, 6, 8 would be the next number of bounding sides. So maybe this 4th dimensional thing would have 8 bounding sides, which would be 3-dimensional things. And how could you make it? You could take a cube and you could move it somehow into another dimension, which we don't understand, and join all those together, and that would give you this 4 cube. Sphere says, that's nonsense. Don't be stupid. But it isn't nonsense, and here is a hypercube shown on the slide. Now, of course, this is a projection into 2 dimensions of a 4-dimensional thing. So the lines don't look all the same length, just like the lines on a cube don't look all the same length in our 2-dimensional drawing, but we say that they are. So what I portrayed it as here is like a 1 cube, and then a smaller one looks like it's inside, but of course it's not really, and we just can't draw that 4th dimension very easily, but it's a projection. So you imagine those 2 cubes joined together, and they are making each pair of squares there, each pair of square faces on the cube, in that transition will make a cube itself. So you've got the inner cube and the outer cube, and then the 6 cubes that are passing between the 2 of them. So this does have 8 bounding cubes, and it does have 16 vertices, and we call this a hypercube now, or some people call it a tesseract. And the 4th dimension definitely, is something we consider in mathematics. And this is what Abbot was aiming at by analogy to help people to understand that just as, a 2-dimensional being might struggle with the 3rd dimension, but it does exist, we 3-dimensional beings might struggle with the 4th dimension, but it does exist and it all works and the maths works. Now, it's interesting to ask, why would this clergyman head teacher suddenly be writing about the 4th dimension? And there are several reasons for this. It was really a hot topic at the time. It's very much in the air at the time. And there are lots of reasons kind of joining together to make this be the time when the 4th dimension got kind of public traction. So I've just done a few of these. So if we sort of think about, in the centre of that slide in the middle, there is geometry. And for a long time, what is geometry for? It is, the actual word means measurement of the earth. You use it for surveying, you use it for all sorts of things. But, you're using it, it's coming from a practical understanding. And when you're doing practical surveying, you don't need to know about the 4th dimension. You wouldn't even ask about it. It's not a thing that comes into your mind to ask. So from the origins of geometry, we then move on, and we have developments in other areas of mathematics as well. So one thing is algebra. So algebra was developing, and people started to write down things like variables and equations, and the notation developed until we were quite happy writing things like x to the 4, x to the 5. And the notation for doing that became such that it was just as easy to write x to the power 17 as it is to write x squared. So then you might say there's sort of a lag, but could x to the 17 mean anything? I mean, we know that x squared is the area of a square of side x. X cubed is the area, the volume of a cube of side x. what's x to the 4? Does that have a geometrical interpretation? So there's that. Other things are coming in the 19th century. So for a long time, as you probably know, there'd been, for thousands of years, there'd been this sort of concern about the parallel postulate of Euclidean geometry. So in Euclid's Elements, there are these postulates, various rules, that most of them are completely that's something I'm happy to work with as an axiom. But this parallel postulate, which one way of expressing is that if you have a line and a point not on the line, then there is a unique line through this point parallel to the original line. Now that is something we are supposed to just take as true for Euclid's Elements, and then we prove all these other theorems based off of those 5 initial postulates. But it was always something that people were sort of worried about because it didn't seem as obvious as the other ones, which seemed quite self-evident. So lots of people tried to prove this 5th postulate, the parallel postulate, from the other 4, couldn't do it. And then people started to realize actually it doesn't seem to be provable from them. And in the 19th century, several people, various sort of working independently, discovered that actually you could have non-Euclidean geometries where the parallel postulate didn't hold, but the other ones kind of did. And one example of this is in spherical geometry, where I'm showing a picture of the world, and if you draw a triangle which is like 1/8 of the Earth's surface, that is a triangle with 3 right angles in it. The angles in a triangle on a sphere don't add up to 180 degrees, they add up to more than 180 degrees. And if you kind of set things up properly, you have to have the idea of what lines might be, because you can't actually draw a straight line on a sphere. So this is not contradicting Euclidean geometry, it's just a different concept, where the lines actually now are great circles, for example, equators. So there's these kinds of different geometries are coming in, which sort of expands the minds a bit, and we think, maybe there are more things that we could do with this geometry. And other things are happening too. So in physics, increasingly, things like electromagnetic fields are coming in, which need to be described. They describe various properties that the points can hold. So if you're in an electromagnetic field, you've got your position, but you also have what the electromagnetic force is at that point in the field, and it has a direction. So you're associating more numbers to that point than the 3 numbers of its coordinates in space. And this is something we do much more nowadays, much more naturally as well. We think of dimensions as really just degrees of freedom nowadays. So if you're describing a weather system, then at any one point you've got the point's position, but you might also have the temperature, the barometric pressure, the wind speed and direction. All of those things you can just associate to that point, and you can just add them as extra coordinates right to that point. So this is sort of thinking in higher dimensions in a very natural way now to us. Another thing that was happening around this time was in algebra, but based on trying to understand how we can manipulate high-dimensional coordinates, higher than 2, right? 3-dimensional coordinates. The mathematician William Rowan Hamilton had sort of codified how we represent complex numbers, which are numbers that involve the square root of -1. You need those to solve even quadratic equations. How can this enables you to do algebra with 2-dimensional numbers. What about 3 dimensions? And when he actually finally solved this problem, what he came up with were these things called quaternions, which require actually 4 dimensions to be able to do this algebra. So these quaternions are giving you another sort of impetus to study the 4th dimension. So all of these things were happening and coalescing in the 19th century, and the 4th dimension became a big topic. Lots of other people were actually writing about the 4th dimension and higher dimensions, and it became, even in the public imagination, quite a popular thing. So you've got people like Charles Howard Hinton, who he wrote a little pamphlet, What's the 4th Dimension, in 1880s, just before Flatland came out. It was later republished by the publisher put the subtitle Ghosts Explained, because one theory about how ghosts could move in and out of houses and go through walls and stuff is, as encapsulated in a nice little quote from The Canterville Ghost by Oscar Wilde. He's describing the ghost. He's in a bit of a pickle. There was evidently no time to be lost. So hastily adopting the 4th dimension of space as a means of escape, he vanished through the wainscoting and the house became quite quiet. So just like the sphere in Flatland, he can just move out. He can move into the 4th dimension, move around wherever he wants, and then come back in wherever he likes. This is how ghosts move through walls, right? So this is even becoming a kind of a popular thing that people understand in the 4th dimension. Lots of sequels things that followed from Flatland, things inspired by Flatland. I've just written a few of those down and I put links to them in the transcript. So Hinton wrote about another version of a Flatland. It was actually a two-dimensional planet. So the beings lived on the surface of this two-dimensional planet. So they were kind of essentially moving around on a line, but kind of further. And so they had up and down and east and west, but they didn't have north and south. So that planet Astria. Then you've got people like Dionys Berger, who wrote Bolland or Sphereland in English in 1957. The one we're going to talk about is the Planiverse or the Planiverse by A.K. Dewdney. That came out in 1984, 100 years after Flatland. But other people who have written sequels or books leaning on from it, Rudy Rucker wrote The Fourth Dimension in 1985, and Ian Stewart, former Gresham Professor of Geometry, in 2001, Flatterland, and he also wrote an annotated Flatland, which is a really useful guide to Flatland itself, which I strongly recommend. Let's talk about the Planiverse. So this is a 1984 book by A.K. Dewdney, and it's a serious attempt, probably the most serious of any of these books I mentioned, attempt to understand not the fourth dimension, but what life would be like actually if there really were a two-dimensional universe. So this is a kind of a real intellectual effort here. How could things work? Because, as you can see on the slide, there are lots and lots of things that we have to consider that would have to work differently from our three-dimensional world. So I just mentioned a few of these here. So the setup of this book is that Dewdney is doing a computer science project with his students, and they create this two-dimensional universe on the computer, and they have to set up the various rules of what life is like. So they, for example, decide that gravity in a two-dimensional, so this isn't a two-dimensional world within our universe, it's a totally different universe. Okay, so there is no third dimension in this universe. So what would gravity, for example, be like? Well, remember earlier we had mentioned that, if you have a planet of a constant density and you scale it up or down in radius, the gravitational pull on the surface of that planet is proportional to the radius. So in a two-dimensional world, if we kept the inverse square law of gravity, that wouldn't be true anymore, because the area, the mass of the planet would be proportional to its area, which increases with the square of the radius. But so if we kept the inverse square law, then actually the gravity would be constant on the planet of any size. So this kind of works better, or at least you preserve that rule about the gravitational force being proportional to the radius of the planet if you have not an inverse square law but an inverse linear law. So this is what they propose, for example, for gravity. So physics is a bit different. Chemistry is a bit different as well, because if you imagine, how do molecules form? Now, some of the configurations of molecules in our universe involve three-dimensional molecules. And, you could, in theory, you could squash some of them flat or have them on the plane, but you can't do that with all of them. Some molecules actually have to be three-dimensional, and those molecules then couldn't exist in this universe. There are much more details gone into the chemistry in this book, and if you're interested, I'd suggest you go and look at it, because it's really very detailed analysis of what might happen in such a world. Another thing is that just like in our world, we have molecules that are kind of 3D mirror images of each other that you can't rotate to make them become like each other. It's called the phenomenon of chirality handedness of molecules. You have a similar kind of thing, more extreme in the two-dimensional world, where there are some things that in our world we could just rotate into each other, but in two dimensions this would be only accomplishable by reflection, which cannot be done physically. And so the chemistry is going to be different. The biology is different as well. I'm working up the slide, actually not down, but the biology is going to be different too. And it doesn't take long to see why. For example, our digestive tracts run all the way through our body. But if you just have a completely flat organism in two dimensions, any line that moves straight through the body would just cut the body in half. You just fall into two pieces. So that can't be what happens with the organisms in this flat world. So you can't have tubes or anything like that, or the body just falls into two parts. So what they invented for this book was this idea of zipper organs, where actually they sort of open and close, and so sort of bubbles of liquid or fluid can pass through, and then the tube, it's not a tube, it just closes up after itself. So it's kind of moving through the body like that. They also, the creatures in this world, have to have exoskeletons, not endoskeletons, because otherwise, the bones would keep getting in the way of things trying to move in between. So when we're talking about these things that have to be true, the way the book is set up is that the students set up this simulated universe, and then suddenly through some kind of weird universal morphic resonance or something that we don't understand, suddenly their computer program is sort of invaded by this person or this creature, Yendred, who is from an actual two-dimensional universe that somehow there's this way of communicating within the simulated computer universe that we've created. So they start talking to this Yendred, who is from a real two-dimensional universe, and he lives on this planet Arda, and life is described for him. So they can see his planet, and of course they can see everything because it's two-dimensional. They can see inside him and all of this stuff. So a lot of writing is about how things are in this world. Yendred, by the way, does look awfully much like Dewdney backwards. So this is an indication that this didn't really happen, even though it is written as if it happened. So these people, they live on the surface of this planet Arda, and it's a circular planet. It's in two-dimensional world. So we've got the interior of the planet, which they live underneath the surface. And you can see why, because if you're walking around a line, which is the surface of the planet, you can't walk around people or objects or obstacles or buildings. You have to, if two of these people bump into each other, then one has to climb over the other. There are various social conventions about who climbs over who. So, of course, then you want the buildings underground. And, these people, the Ardeans, what are they viewing? Their vision is entirely just a line. From they look down at their feet and they can just move their heads up and down. They're quite symmetrical because you could never turn around and face the other way in the same sense that we could. So their vision, they're just looking up and then their heads can move all the way around. So it's a really interesting thought process to try and work out what life would be like and how things could really work. And it's absolutely amazing what Dewdney managed to do in terms of thinking through how things could be. So I'm just going to show you here. This is a picture of a house on this world. And if you think, how would a house be? So it's under the ground. So how do I actually get in to my house? So I've got to be able to find a way to not leave holes on the surface so people can fall through, but I've got to be able to get down and then get out again. So if you think about where stairs can be, in our houses, we can have some stairs, but you can walk around the stairs. In a two-dimensional house, if you put some stairs and they're not movable, then they just split the house in two and you can never get past them. So all their stairs, or the tops and bottoms of the stairs, have to be sort of able to be lifted up and down. So when you want to enter your house, say you're walking in, and so there's some stairs go down, and then that's fine. But if you want to walk past the house without going into it, you've got these movable stairs, so you walk on, and it kind of goes down, and then you go down a little bit, and then you just join up the stairs on the other side. So all these little considerations are really carefully done in the book. It's a really interesting read. So these are some of the ways in which Flatland has inspired many, many writers over a long time. Some of those thoughts about the fourth and high dimensions are just as pertinent now. So that's what I wanted to say about Flatland and all of its successors. But I just want to finish in the last few minutes by talking about some of the ways in which writers have used mathematical metaphors and ideas just in their writing in standard books, so to speak. So this, Planiverse sets out to be an understanding of a two-dimensional world. But I mean just in writing a work of fiction, and you're looking for a metaphor to use, and what comes into your mind is something mathematical. Now, some authors do this a lot, and I know my suggestion is this really is because they like maths. And once you've got maths in your armory of possible metaphors, then of course you're going to use it. The first of these is George Eliot. So she loved mathematics. She used it as a solace in times of trouble. So she's got this letter that she wrote to friends when she's had a difficult time, and she's helping herself feel better. I take walks, I play on the piano, I read Voltaire, I talk to my friends, and I just take a dose of mathematics every day just to help her feel better. And there are lots of mathematical metaphors in her books. Next time you want to read a George Eliot book, just have a look, and she uses these just mathematical thoughts. So here's a description of Mr. Casson from Adam Bede. He's a landlord of the local village pub. His person was by no means of that common type which can be allowed to pass without description. On a front view, it appeared to consist principally of two spheres, bearing the same relation to each other as the earth and the moon. That is to say, the lower sphere might be said at a rough guess to be 13 times larger than the upper. Now, this is an interesting, you can immediately see, yes, this is a nice comparison. But what's interesting is this number 13. So this is not the ratio of the diameter of the moon to the diameter of the earth. It's about 1 to 4 or something. It's not the volumes. That's a different ratio again. But I think it makes sense what she's chosen 13, because when we're looking at a picture, probably what we instinctively are seeing is the ratio of areas. And that is indeed about right. The cross-sectional area of the moon to the earth is about 1 to 13.45. And you can see I've just superimposed those there. That's a really, pretty good approximation there to Mr. Casson and the Earth and the Moon. What's interesting is you have to know these things quite accurately to get that 1 to 13. Because if you approximate less than about 3 significant figures for the values of the radiuses of the Earth and the Moon, you get 1 to 14. So she knew these numbers, she knew what those were, she knew them accurately enough, and this was the metaphor that came into her head. So this sort of tells you, she was mathematical. Adam Bede also finds mathematics a solace. The square of 4 is 16, and you must lengthen your lever in proportion to your weight. That's as true when a man's miserable as when he's happy. This too shall pass, and maths will still be there. Okay, Tom Stoppard next up in our little stop tour. So there's loads of maths in his plays, and in particular, the play Arcadia has all sorts of lovely mathematical treats in it. Honourable mention also to Rosencrantz and Guildenstern Are Dead, which has this theme of them constantly tossing a coin and it keeps coming up heads, and the laws of probability sort of say that's okay, but it doesn't feel right, and what does that all mean? But let's talk about Arcadia for a minute. So it has action sort of in the then present day and in about 1810, somewhere around then, and it's got this young girl she's a nobleman's daughter in a big country house, and she works with her tutor, and she has this mathematical talent. And one thing she's talking about is if you can have a mathematical equation for a bell curve, the Gaussian bell curve, normal distribution, if you can do that, why can't you have one for a blue bell? And she tries to do this, and she's got this little thing. She says, I, Thomasina Coverley, have found a truly wonderful method whereby all the forms of nature must give up their numerical secrets and draw themselves through numbers alone. This margin being too mean for my purpose. That's a reference to Fermat's last theorem. Fermat wrote this in a book that he'd got a lovely proof, but didn't have room to contain it. The reader must look elsewhere for the new geometry of irregular forms by Thomasina Coverley. And what she was talking about was using repetition and iteration to produce things that look like plants. And this, of course, now we know we do this with fractals. And I just want to show you a very simple idea and then perhaps a more complicated one. As an example, you take an initial basic shape like this, a forked line, and then you iteratively turn the component parts of that into their own mini forked lines. You have this self-similarity. So this is stage 2. So the two parts of the fork have now turned themselves into little forked lines. Stage 3 happened again. Stage 4, stage 5, stage 6. Okay. So this is a very basic thing, but you can see, potentially it could look a bit planty. If you take a more complicated initial step like this, then you can do the same sort of process. Stage 2, stage 3, 4, 5, 6. And that really does look like a plant, a fern or something like that. So this really now, we do understand this as one of the ways in which nature is kind of making these plant forms. So this is a beautiful play, and it's got some wonderful mathematical ideas in it. Finally, Moby Dick. So Herman Melville, again, he really liked mathematics. You can see it in his books. He uses, when he's reaching for an allusion or a metaphor, he'll often pick a mathematical one. Moby Dick, in particular, I think, has just loads of lovely, juicy mathematics in it. I'll just mention a couple of things. He's got these things when Ahab's talking about this cabin boy that's really loyal and faithful. He says, "Thou art true as the circumference to the centre." He uses these mathematical ideas. One lovely metaphor is he sees a whale. So this is an orca, but I think he was talking about a sperm whale in the book. And he talks about that the fin of the whale, this isolated fin, It's like a gnomon on a sundial, like cast shadows. It may very well be supposed that the watery circle surrounding it somewhat resembles a dial with its style and wavy outlines graved on it. So this is a really nice little metaphor about a sundial, the gnomon of a sundial looking like a whale's fin. The kind of really, really amazing one is his discussion of the tripods. So these are on a whaling ship, you're boiling down the whale blubber, and you have to clean these tripods obviously regularly. And he said, so they sort of standing in the tripods because they're very big and they're using the soapstone to clean them. And he said, I was struck by the remarkable fact that in geometry, all bodies gliding along the cycloid, my soapstone, for example, will descend from any point in precisely the same time. So what's that about? I mean, this is not something that you would necessarily study in school geometry. So this, Melville must have gone a bit above and beyond, really. So here's the picture, and you've got, this is a cycloid. Okay, so the cycloid is the curve made by a rolling circle, and you follow the path of a point of the circle as it moves along, and it produces this curve, which is a cycloid. So we can make the equation for that, and this was a problem first, the equation for a cycloid and its relationship to this problem of a curve where bodies would fall in the same time, no matter where they were dropped from. Huygens did a lot of the work on this, but here's the equation of a cycloid if you want to go and try and draw one. And it's, you can plot the points and they depend on the sine curve and cos curve, and you relate them in this particular way. And if you take this cycloid and you just, take the portion of it between 0 and 2 pi and turn it upside down, this is this cycloid shape. And I've got there a little point on the slide. It's wherever you release that point from, it will slide to the bottom in precisely the same amount of time. So this is the cycloid property that Melville is talking about. I think that shows a real level of mathematical knowledge beyond the usual. So these are some of the ways in which we see mathematics in fiction and some of the ways we can take mathematical ideas and run with them. Now, there's another way, as I've said, that mathematical structures can appear in fiction, and that is in the structure of the fiction itself. That is the topic of my next talk in this series, Mathematical Structures in Fiction. So I'd encourage you to come to that. It's on the 9th of March at 1 p.m. You can sign up at Gresham, as usual. For now, I'll be around in the live chat so I can answer your questions that you've had during this talk there, and I'll do my best to answer those as well as I can. I hope you sign up for the next time, and I look forward to seeing you then.